In this video, we are going to take a look at indefinite integrals and the substitution method. So as a reminder, the indefinite integral is the antiderivative. It is the integral without our lower and upper limits of integration, which again is just our general antiderivative. So in this section, we will look at our first technique for solving integrals. Or in other words, antiderivatives. If we recall, it might be difficult to find a definite integral in general, but if we know an antiderivative, we can solve that kind of a problem, a definite integral problem. And so we're going to practice finding antiderivatives now. If we know directly a derivative of some function, like the derivative of cosine is negative sine, so if we ever wanted to integrate negative sine, we could just get cosine. And that would be straightforward and relatively simple. But many functions are not obvious what they are the derivative of, so it is not easy to see how to take the antiderivative. So here in this section, we're going to take a look at our first method for how we might be able to do that. This method will not work all of the time, and in fact, finding integrals are difficult and not always possible. At least antiderivatives are not always possible in the methods that you might think. So we have to come up with several different techniques and hope one of them works. And again, we'll look at our first technique here now. So first thing I'd like to do is recall a specific type of derivative that we've seen a lot here. If u is a differentiable function of x, and n does not equal -1, then the derivative with respect to x of u to the n plus 1 over n plus 1 is just equal to u to the n times du dx by the chain rule. All right, we take the derivative of u to the n plus 1 over n plus 1, and we multiply by n plus 1 here. That cancels this denominator out. And we subtract 1 from the exponent, so we just get u to the n. But then u is a function of x, and we're deriving with respect to x, so we then need to multiply by the derivative of u with respect to x. And so we get this. Well, what does that tell us? That tells us we can take the antiderivative of u to the n du dx, all with respect to x. If we take the antiderivative with respect to x, we get back to what we started with, which is u to the n plus 1 over n plus 1, but of course with some addition of a constant c out there. Or equivalently, if we wanted to write our integral in terms of u and integrate with respect to u, then this is the integral of u to the n du, and that is u to the n plus 1 over n plus 1, all plus c, some constant c. So here we're using differentials as our notation when we're taking integrals. And this du dx times our differential dx, we can just think of as the differential du. Let's go ahead and explore this a little further with an example. And that example is to find the integral x cubed plus x all raised to the fifth times 3x squared plus 1 dx. We want to solve this integral. The first thing you want to do is you want to notice that here we have a function raised to the fifth power, and then we have the derivative of that function outside of that. So if we suppose u is equal to x cubed plus x, so this is our change of variables that we're going to make, u is equal to x cubed plus x, then we get that du is our derivative here, so 3x squared plus 1 times dx, thinking again in terms of our differentials. And so, using this change of variables, we get the integral of x cubed plus x to the fifth, 3x squared plus 1 dx is all equal to the integral from u to the fifth du, right? This was u raised to the fifth, and this part out here we substituted in du for that. Well, this is an integral we know how to take. This is just u to the sixth over 6 plus some constant c. And we don't want our integral in terms of u because we started with a function of x, so we just substitute what u is back into the function. So this is now x cubed plus x to the sixth power over 6 plus some constant c. And now we have our integral in terms of x. And so what you would see here is if you take the derivative of this function here, you end up with x cubed plus x to the fifth times 3x squared plus 1. So what happens here is we essentially reversed a chain rule. That is what our substitution rule or substitution method is all about. It is about reversing our chain rule. So let's go ahead and write that down, and that'll be the last thing we do in this video. What is our general substitution rule? So our substitution rule is as follows. If u equal to g of x is a differentiable function whose range is some interval I and f is continuous on I, then the integral of f of g of x times g prime of x dx is just the integral of f of u du, right? This is f of u, since u is g of x. And then times, well, what is g prime of x dx? That is our derivative of u, which we're going to use the notation du here. So du is just g prime of x dx, again thinking in terms of differentials. And so this is our substitution method. Stay tuned for the next video where we're going to do several examples using this idea.